Hello, everyone. Welcome to Algebra. I'm excited to be able to do this video for the first one. This will be your Monday video and just something that we're going to get used to seeing. This is me recording at home. Sometimes I'll be recording at school. Depends on how much I got done the week before. As you can see, I was behind last week, so we're going to do this one at home. So we're going to talk today a little bit about operations with rational and irrational numbers. Just a quick review of what rational and irrationals are. We're going to talk about sets of numbers and kind of what that looks like. Okay, so first let's talk about what a set is. A set is just a group of numbers. So, right, I might have like set A, and typically sets are in these like really cute curly Q brackets, which I remember practicing in the middle of math class if I'd get bored, because people would make really pretty ones, and I wanted to make really pretty ones. So it kind of looks like this. Mine are okay. Sets. So let's say we have a set. Let's just go 1 through 10, right? Of just integers. Right? So we have the set A, it's 1 through 10. Typically in sets, numbers are written in order, numerically ascending. But anything could be a set, right? You could have a set of just one number. That's still a set. And inside of sets, we can have subsets. So for example, inside of set A here, maybe I have set B, which is a subset of A. And let's say that set B is all the even numbers. So set B would be only the numbers, because it's a subset, is only the numbers that are in set A, but it's the even ones. So in set B, I'd have 2, 4, 6, 8, 10. So set B is a subset of A. That's just the evens from set A. And I could have multiple subsets. I could have subsets that have numbers in common, right? So I could maybe say set C is a subset of A also. It's numbers divisible by 5. So set C, oh, that was a terrible curly Q. Okay. Set C is 5, 10. So set C only has 2 numbers, but you can see that subset B, subset C, both have a 10. That's okay. So these sets, when we talk about sets, is just a group of numbers. And you're going to hear, this is kind of how we start classifying things. So for example, like the set of numbers that are prime numbers are a very important set. The set of numbers that are even, divisible by 2, right? So we can use these sets to look at proofs and things like that and say, well, what set of numbers does this work for? So in particular, when we think about numbers and maybe making sets, or just kind of comparing, that makes me think number line, right? If I'm looking at different numbers, maybe I want to compare how they are, what they look like. I'm thinking, well, throw them on a number line, see what they look like. But let's say we have something like 40 elevenths, and we have the square root of 15, and we have I don't know, pi plus 1, for just random examples. One of the things that's problems when we're looking at sets of numbers is it'd be really, really nice when I compare things, I need to make them all look the same, right? So maybe I need a decimal. Maybe I can make them all whole numbers if it's pretty. That would be really, really nice. Maybe I can estimate them and kind of see what they would be approximately. Whatever is going to work for you. So, for example here, this would probably be a really good example of if I turned everything into decimals here. So if I want to compare these, if you can't tell, by estimating or something like that, we can just turn them all into decimals, and then we can see, label them from least to greatest from there. So let's see here. My wife has a calculator. She's off screen. Can you help me out here?
Yep.
Okay, so 40/11ths is not going to be a pretty one, but I can tell that if it was 40/10ths, it would be almost 4, but it's going to be a little bit less than that.
You want the decimal?
Yep.
3.636363.
So we got 3.6363 repeating. Okay. Square root of 15 is also, it's almost a perfect square. We know that square root of 16, 16 is a perfect square. We know that square root is 4 and negative 4. But we're looking at probably just the positive version because we're comparing. And so we know it's going to be a little bit less than 4 also, just like this number.
3.8729.
So 3.8729. And when you guys are comparing these, just kind of cut it off where it makes sense. Like, it's not always going to be great if you go only 2 decimals and then cut it off and you're going to be like, they're the same. They're definitely not the same, right? So if you need to go farther, write more of the decimal. If you don't need to, then feel free to stop. And then pi plus 1, you know, we can use the approximation 3.14 for pi. We add 1 to that. That's going to be 4.14, which, again, it's just an estimate, but we can obviously see that these numbers are in order, least to greatest. So when we're talking about comparing rationals, right? So if we look here, this one is rational. And do you remember what it means to be rational? I wish I could call on you, but you're literally across the screen. Rational numbers are any number we can write as a fraction. And we know that this is a rational number because if we look down here, it has a repeating decimal, right? It has that set that just the same digits are going to repeat. Those are rational numbers. They show a decimal that repeats or a decimal that ends. So square root of 15, we might think, oh, Mr. Odie just wrote this. That means it's rational. But if you put this in your calculator and you tried it, you saw that that decimal just kept going. And calculators are going to cut it off eventually. But pretty much if it fills your screen, you know that's going to be an irrational number. The square root of 15 is irrational. If you remember this from last year, only square roots that are perfect squares are going to give you a rational number. All the rest of square roots are all irrational numbers. So square root of 15 is irrational, and we had to estimate. It's approximately 3.8729, and it's going to keep going. And pi plus 1, we kind of talked about this already, but pi is irrational. So if we take this irrational number and we add 1, I'm going to guess it was we estimated around 4.14. But does that make it rational? If I add 1 to it, because this is a rational number for sure. I could write 1 as a fraction, 1 over 1. But obviously pi I cannot. That's definitely irrational. So that's kind of the question that I want to kind of pose to us today, is to think about these things. And when I do operations with rational numbers and irrational numbers, is there some kind of outcome that happens where I know it's going to be rational and it's going to be irrational? I'm not going to answer this one. We're going to talk about it. So I think you should feel okay with the ordering. Again, just kind of put those in your calculator. But let's talk a little bit about rational and irrational operations. Which one do I have here first? The first one in your book example is if you add 2 rational numbers. So let's say I have 2/3 plus 7/8. If I do that, am I going to end with a rational number? This is me giving you time to think of what you actually think is going to be true. Did you come up with something? All right. So, first of all, if I wanted to add these, Do you guys remember how to add these? Hopefully you know common denominator, right? We definitely need to get a common denominator if we want to add these. And I'm going to kind of just do this one out because then I'm going to do the rest of them in kind of a general form. And then you can see like the difference between if I put numbers in there or if I'm just going to have variables that count for numbers there. Okay? So if I wanted to add these up, 3 and 8, probably you're thinking 24. Make them 24. So I'm going to multiply this one by 8s. I'm going to multiply this one by 3s. That's going to be 16 24ths plus 21 24ths. And remember, when we add with common denominators, we keep the denominator, but we're going to have 37 24ths. So as you can see, we added two fractions. We got a fraction. So obviously that number could be written as a fraction. When I add two rationals, I am always going to get another rational number. Sure, makes sense, right? So pretty interesting. Or you might think that's kind of boring. I would know that. Sure you can. But part B says, what if we add, if we multiply two rational numbers, is that always going to give me a rational? Well, you're probably thinking in your head, so far I've done a lot of multiplying of rational numbers. Sure you have. Did I always get rational numbers? Well, probably you're thinking yes, but let's see if there's a case where it doesn't happen. So let's just call this rational a over b. It's a fraction, so that's why I chose a over b. One thing that is important when I do this, make sure you guys know that anytime I have a variable in the denominator, I have to assume that it's not 0. Because we can't have 0 in the bottom of fractions. It's an indeterminate, which you guys probably don't know that, but it's definitely an error. If you put that in your calculator, anything over 0 you cannot do. So we'll call this one a over b, and we want to multiply that by c over d. And again, d can't be 0. And we're thinking to ourselves, is that going to give me a rational number? Well, let's see here. If you remember how to multiply with fractions, you go straight across. So if I did a times c, that's just going to give me ac. If I do b times d, that's going to give me bd. And remember, these can't be 0, so that means the product of this can't be 0. So if I'm left with ac over bd, that is still in fraction form. So yes, if I multiply two numbers that are rational, you always are going to get a rational outcome. The product will always be rational. So those ones kind of make sense, right? You guys have been doing that since 2nd grade, where you multiply or you add two numbers that you know are rational numbers. You might not have known they were called rational numbers, but now you know why they are, hopefully, because we can write them as fractions, and then I can get a fraction back out. So what happens if we introduce a case where one of them is not rational? What is that going to change? Let's talk about addition first. Yeah. Let me check your book here. They do, yeah, sum first. Okay, so here's what this is going to look like. So we're going to have a rational number. We're going to call that a over b. Again, we have the fraction. B cannot be 0, which is important to note. And an irrational number we can't write as a fraction. We're just going to call it c. That's what your book chooses. We don't know what it looks like, but we do know it cannot be a fraction. Because irrational numbers are not fractions. So, what we're going to do is we're going to assume something this time. Let's assume that when I add these two things together, I'm going to get a rational number. So if I added a rational and an irrational, let's assume we get some number that is rational. I think, does your book use D and E? It uses P and Q. Let's use P and Q. So we're going to assume that it gives us P over Q. So some rational plus an irrational, we're going to assume gives me a rational. And we're going to put a question mark over that because it's an assumption that we're going to make. Yeah, so let's go from there. Well, if this is true, let's go backwards, right? Let's solve this equation for C and see what the irrational number would have to look like and see if that makes sense. So if I want to solve this for C, that means I'm going to have to subtract A over B from both sides, which I can do. That's just some number, right? So that gives me C equals P over Q minus A over B. Don't get my A confused. Sometimes I make the little stem a little too long. It looks confusing. A over B. Okay. So if I want to subtract these, same idea that we did in the first example, we need common denominators here if we want to actually figure this out. So if I want P over Q and A over B to have the same denominator, probably the easiest thing is to take this denominator with this one, take this denominator, multiply it by this one. So let's multiply this one by B over B. Let's multiply this one by Q over Q. And that would give me BP over BQ. Too bad it wasn't another B and then it'd be BBQ. That sounds delicious. And then over here we'd have AQ over BQ. Okay? Does that make sense to everybody? Getting that? We have common denominators. We multiply this one by the B's. We multiply this one by the Q's. Now we can actually keep the C here. That's important. Now we can actually subtract these things, and you're probably thinking like, I don't know how to subtract that. Don't worry about it. Just do BP. Can you guys see this on the video? Yeah, okay. BP minus AQ. We don't have to know what that number is, but what we do know is that when we subtract it, on the bottom is just going to be BQ. And I don't know about you, but that sure looks like a fraction to me. We have some number over some other number. So here's the deal. This is called a proof by contradiction. What we did is we assumed that when we did a rational plus an irrational, we're going to get something that is in fraction form. But when we undid that, right, when we used a little bit of math and solved through, we got down here, and it says that this irrational number is actually a rational number. And I don't know about you, but I bet you can tell that's not true. This irrational number cannot be in the form of this. So since that part's not true, then guess what? Our assumption at the beginning is not true. So from this, even though it looks confusing, what we did was we showed that a rational plus an irrational is not going to be rational. The sum of those things is going to be irrational, because this does not make sense. If the math would have worked out and it would have made sense, then we could have said our assumption was correct, and we could have went from there. But we cannot say that. This is a proof by contradiction, not a true statement. And you're going to find, if you look in example 4 in your online book in section 1.1, you're going to see this was the first part. The second part has to do with the product of these things. And I think I'm just going to let you look at that one and see, hopefully kind of do this with that and see that it doesn't make sense as well. So on your homework, they're going to give you some thinky ones, where you're going to have to think like, hey, is this going to be rational or is this going to be irrational? And I'll kind of comment back and talk to you guys a little bit on that to see what you think and how I can prove to you one way or the other. All right, so I'm going to try to keep these videos relatively short, just because I know, it's a lot to just watch a video, and I don't want to if it's too long, I know I'm going to lose you and stuff like that. So I think I'm just going to stop it there and let you do some practice. And then, as always, if you have anything like questions, feedback, send me a reminder, send me an email, and we can definitely work out whatever. But it is going to be a little bit, and this is how I would be if I was in the classroom with you, is that I like to let you figure some stuff out, work through it. If you don't on the other end, we can have that conversation and say, well, this is what this is what it looks like. But definitely I like to make you think. And so even though you guys are stuck at home, and I'm, far away from you, I'm still going to try to challenge you to make you think through some of these things. All right, so that's lesson for today. Again, you can always check out your ebook too, look through all these examples. I actually tried to do the same ones in the book so that you could look at it along with the video. You can hit me back if you think that's helpful, or if you'd rather see different ones, different numbers and different examples. Let me know that too, and we can try to figure those things out. All right, we'll see you guys later.